Hello students. So today's class we'll start off with the new chapter, that is unit 3, design of keys and couplings. Essentially keys, joints and couplings. So joints, couplings, maybe can put it into a single portion. So we'll have an introductory class today, and maybe solve some simple problems on keys. This unit is fairly simple because you have preset procedures. Keys is obviously very simple. It's only uh, one or two, maybe up to three formulas maximum you need to memorize. That too, it's there in your dead end books. So that's regarding keys and couplings. There are set procedures. So you have a detailed set of procedures, design procedure which you can follow and design the entire coupling. Okay. So this class we just talk about what is a key and what is a coupling, where it is used and stuff, right? So key is used in a connection. So as you can see in the figure, this maybe a bush kind of a thing, which is connecting to the two shafts. Okay, in order to avoid the intermittent motion, the relative motion between the edges. So this is usually used in assemblies, in transmission shafts, gears, and gear to shaft, shaft to gear. So this kind of arrangement wherever we are doing, so those places we use something called as key. So what you see here on the picture is called a key slot. Okay, this is not actually a key. This is a hollow shaft. You have a hollow shaft in which there is a key slot milled directly to. So a key is the one which sits inside this slot over here. Okay, so maybe a key will just come sit inside this portion right here. Okay, so it may come sit over here. Okay, and it'll run throughout this length. Okay, run throughout this length and maybe close out. So rest of the portion will again sit in another shaft. Okay, like that. So that's where the keys will use its function. That's where it is used, right? So it avoids this relative motion between these two shafts and no, even gears, shaft and gear and shaft, and even between two shafts which are concentrically assembled. And the function, as I told you, you have the hub which is encompassing the shaft. The key is usually as used as a connection between these two things, the hub and the shaft. So it is used as a temporary joint kind of a thing. So it should provide relative motion in this direction, that is the x direction. So in x direction, you have a relative motion. You can easily replace and stuff. So why we are not making this fixed is that if there is excessive forces or excessive torque being applied to the shaft, there is a possibility that it may overheat or it may jam inside the hub. So both these are expensive in terms of material and manufacturing. So these are expensive, and you cannot afford to lose these two just for the sake of some excessive torque or something. So that's why key is provided as a fail-safe. So it's provided as a fail-safe, and therefore, whenever there is an excessive torque or something being applied between the shaft and the hub, no, the key breaks. The key breaks, thereby you can replace it very easily. Okay, so that's the one of the advantages of. There's some problem with the design, I guess. Now it's quite okay. So that's the function. That's the main primary function. These two are the main primary functions the key performs. That is, it is, you know, is mainly used for transmitting torque. Okay, from shaft to hub or hub to shaft, vice versa. Secondary function is relative motion. So it locks the motion between these two, and it avoids in terms of gear and pulley. No relative motion. It acts as a single body, right? So also sometimes it is also used between gears, between maybe hub and shaft. Sometimes it is used between hub and shaft. Sometimes between gear and the gear pulley, transmission shafts. These are the general applications of a key. Okay. So key usually will be cuboidal in nature. So different length, breadth, and right, depending on cross section, we have different names and stuff. So coming to classification, you might get some theory or theory questions based on this, right? So this is you have sunk key, saddle, tangent, Kennedy, all these different types of names are there. So even in data handbook, you will find all these names. Not worry. So basically, the difference here is usage and appearance and how the key looks like. Okay. So I'll just go through one by one in a brief way. If you take the first one, that is a sunk key, it is halfway. So the name suggests it is sunk. Sunk means it is dipped halfway, like okay, halfway inside one of the shaft and halfway inside the other of the hub or even gear. So it is like half and half. Exactly halfway, it is assembled between two rotating components, maybe shaft and gear and stuff. So among these, there are different uh, categories, types of sunk key. The first one is again subdivided into many other types, maybe rectangular, square. These two are depending on the cross section, and you have parallel key, jib head, feather, and wood rough. So I'll explain each one, I guess. Yeah, the first one, rectangular key. Rectangular key, you can see the cross section will be rectangular. Okay, width will be 4, diameter divided by 4, and thickness will be 2 times width by 3, or diameter by 6. So these are the standard values which are there in the data handbook also. So some standard is maintained here in case of a rectangular key, and also it is tapered. You can see standard 1:100 taper is provided so that it facilitates easy removal. Suppose it is broken or it is worn out or something like that, so then you can remove it easily. Okay, again some error in the formatting. I think this is a square key. Square key where the difference is just this square. The cross section here, which you see, is just a square thing. Okay, so the cross section here will be like a square. Okay, so that's the only difference. That's the only difference, and manufacturing flexibility, easier to manufacture, and so that's the advantage of this. And jib head, as the name suggests, you have a jib head. Okay, this wedge shaped head you see is called a jib. So this jib facilitates easy pressing and remove. And as you can see, this is also tapered. So it may be either rectangular, mostly rectangular sunk key. So for easy removal and fixing applications, you have this jib head key. Again, dimensions you can see similar to the rectangular one. And feather key is like it prevents relative motion in terms of rotation also. So it is rigidly bolted using set screws. It is rigidly bolted onto two ends of the shaft, and also facilitates easy removal, but only manufacturing constraint. So this can be used as a rectangular or even circular fashion. So sometimes it's bolted, sometimes it is also having the head which is locking into positions. So this is, I think, practically a little bit difficult because you have certain tolerance need to be maintained if it has to be mounted. So this flange and the shaft has to be accurately machined or placed, and yeah, it will be tight in case of a jib head one. And in case of feather key, it's I think fairly simple. You can just drill holes and tap it in order to fix it on either side. And woodruff key. Woodruff keys are like they're with a radius. So you can see the first figure over here. You have a curved portion, and you can see here there's a two triangles. Two triangle finish is like a grinding finish. So you grind it, or milling using a very small cutter. So that's a two triangle finish. You have to have similar uh, female portion. So this you can call it as a male jib head. A female jib also has to, woodruff also has to be cut inside the shaft. Okay, so that you can insert this woodruff key inside that radius counter, and thereby securing both shaft and the hub. So this is front view, which is shown. You can see the woodruff key is protruding out of that radius portion of the shaft, and it is locking into the hub. Okay, usually it is milled by using a horizontal milling cutter. So it is directly sunk inside shaft, and thereby it will provide for easy seating. Okay. So this does not provide any relative motion in x or rotation direction. So it arrests a lot of degrees of freedom for the material. In that way, it is stronger. But at the downside, the manufacturing, right? So manufacturing is a little takes more process. So this cutter is really small, and you need to manufacture this also very accurately and very smooth and stuff. So how do you manufacture this? It's a bit tedious, and manufacturing takes some amount of time and energy. But on the other side, you have no relative motion, either in x direction or in rotational position. Tangent keys, as the name suggests, it's like a tangent. So it is placed at a tangent to the circle, so where at least one side, right? So this one side, you see, it is like a tangent to that particular circle. So when this side is tangent to that particular circle, and when these two meet, right? So it will be like 90 degrees over here. Okay, these two tangents, when they meet, will be 90 degrees. So that's how they are placed. So the objective here is whenever heavy duty shafts are used, large amount of torque need to be transmitted. So in that time, these kind of tangent keys are used. So to avoid uh, frequent breakages, or to take the shocks. So when you rotate, right, the shocks it will uh, carry that shock in a phased manner, and it has gradual dissipation kind of a property. So that's why tangent keys are used for heavy duty. So, and the downside, you can use it only for one direction. You can't use it in both the directions. Okay, when the shaft is running, you can use it only in one particular. It's like a transmission shaft, right? The transmission shaft runs in only one direction. Okay, the gears is what reverses the motion, but most commonly these are used in transmission shafts. Next, Kennedy key. Kennedy key has similar to the tangent keys, but it is placed 90 degrees apart from the center, and there's two square keys. So this is a square key, this is a square key, and this is a square key. So there are two square keys which are placed, and they are tapered. It has two tapered square keys which are inserted at an angle of 90 degrees. Again, heavy duty applications. Whenever there are more than one key, you can directly say that they are used for uh, what do you say, for heavy duty applications. Right. And round key is again a sunk key. So whatever I'm talking about now is called as these are categorized as sunk keys. Most commonly used types of keys where 50-50% are mounted on both shaft and hub. Okay, midway between both. So again, this is also one of the sunk key. It is just a pin, looks like a pin, cylindrical cross section, a circular cross section, and lengthy body, just like a cylinder. looks like. Okay, and drilled holes. A hole is drilled together when we are manufacturing this, together with hub and the shaft. Both are mounted together and they are drilled. So after drilling, you just insert this pin. So usually these pins are called dowels. Okay, they are called double pins. Okay, round key also uses dowels. Okay, and they're drilled and reamed. So reaming here is a 3-triangle finish. I hope you know what the types of finishes are, and this is a 3-triangle finish where very accurate. Okay, if you have you can drill up to 0.01 accuracy, 0.01 accuracy, and very rigid. So that the double pin or the round key, it avoids again relative motion between the two parts, but it has to be like fixed, like press fit together. Not really press fit. It is like a sliding fit kind of a thing. So last one is the spline. So you might have seen this spline shaft. The splines are created in a as a rectangular key. So this is inbuilt into the shaft material. The shoulders are cut and it is built into the shaft material. And since they are inherently the same material, there is no relative motion. You don't have axial motion. You can accommodate. Okay, and you can transmit a lot more torque using this, because this looks like multiple keys, right? Not only you don't have a one single key, you have multiple keys and key slots, so that you have torque very uniformly being transmitted between both the hub and shaft. So usually these kind of gear arrangement is used in wherever you need axial motion also. So wherever you need this to move in and out of this the spline shaft or the splined gear. So in those cases, you use this. So you might use this in milling cutters, milling cutter. So that's how you manufacture these two, that is spline keys and the spline shafts. That's how you accommodate, right? So the indexing operation. So indexing you might have heard in machine shop. So we produce both the spline and the spline shaft using milling operation. Right? So again, uniform torque, very high speeds and good efficiency. On the other hand, manufacturing is it takes a lot of time. So if you're talking about design of a rectangular sunk key, so that's what we'll be doing. We'll be designing only sunk keys of a rectangular or even square type of a sunk key. Okay, so when a keyway is cut into this hub, no, the shaft and the hub, the torque is transmitted by compression on the surface. So you have the key here. So this key will be subjected to compression because there is a hub which is acting on the top. So therefore, this will be subjected to compression. So this can be transmitted as this F1 force here. F1 force, and equal and opposite way, you have F1 force being acting on the opposite side also, right? So you can say on the top surface, you can say this as a AB kind of a thing. So you have that particular surface being acted, and the key compresses and acts, and this tends to shear. Okay, this force trying to press over here, and when it is rotating, there's another force acting over here. So this stress is called as a compressive or crushing. So this stress, whatever is acting here, is called as a crushing stress, or it's a crushing force. Okay, when it is acting, when the top of this hub is acting some amount of weight, and equal in opposite way, the shaft is also trying to push the key. So this is called as a crushing force. And this one more force, when the forces are acting tangentially. So when it is rotating, this shaft here applies a force which is tangential to the that circle, and one more shaft, this hub, what happens is it forces in the opposite direction. So due to this, you have a shearing force. You have a shearing force. So that's how you have two different types of force. Either it is crushing force or shearing force. So depending on these two factors, we design the sunk key. So there are two things we need to consider whenever you are designing the keys. That is crushing force and shearing force. So these are again given by two equations from the data handbook again. So I'll just write, I'll just show you, I guess, show you in the equation where it is and how do we take that. Let me go to the data handbook. Somewhere in 19, I think. I'll just browse through this. You can see as I go on. So these are dimensions of taper key and where they are used, what are the radii required, and all those things. For different, don't worry, we won't use so many factors. We won't consider so many design parameters. We'll only do a few different types of design. I think all of these are related to spline joint. Quarter. So you can see these are joints. Easier to control F, I guess. This is the 19th chapter. 1950 somewhere I can find it. Yeah, here. So width and thickness. You can see here considering two types of stress. So in case of crushing, okay, in case of crushing, you encounter there is the bending. Sorry, in case of crushing, yeah, you encounter there is a bending stress. So this crushing force we equate it equal to the bending stress. That's why in case of crushing, no, we usually take this equation here, the sigma b dash. So what is sigma b dash is? Sigma b dash is a crushing stress. Okay, sigma b dash is the crushing stress, whereas sigma tau here is the shearing stress. So in case of we consider both these shearing and crushing factors. So to find respective dimensions. So these two are the equations which we consider for designing, the keys, especially the rectangular key. These two are the equations which we consider. You can just paste it over here somewhere. So these two equations are the only ones which we consider, right, for design. So this is, as I said, again very simple and stuff. Let's move on. So these are again the derivation part of that. We're not worried much about this. So this talking about what are the forces, crushing area of resistance and crushing stress. So this is how it is. The equation is derived. Okay, not important. Next, we'll move on to coupling. So that's about introduction of keys, the first part. So couplings are the second part of your third unit. So in terms of coupling, no, so there are two shafts arising out of the source and where it will be delivered. So this what you see here. So this part here is a motor which is used in generating that power, and it is transmitting to a device which is using it. Let's say it is a shaft of a lathe machine or anything like that. We can use this to transmit power. So whenever you want to assemble two components together, you use a coupling. So it's inbuilt in the name, I guess. So couple means you need to join some two things, right? So that's what we are doing here. So you have a coupling, in terms of it may be a flange coupling or even flange bush type, pin type. So there are many different types of coupling. We'll go into that later on, but just for now, you know that coupling is a device which connects two shafts, okay, two shafts which are connected in axial. In axial. Okay. Some even provide a little bit of flexibility. We'll talk about that in classification. It is a little bit off. So function. So what is function of a coupling is, as I said, it is to connect two shafts, and it is required to transfer the torque. So it is using even in case of connecting two different shafts that are axially loaded, okay, axial or even torque in case of torque applications, right? And transmission of vibration and shocks. That also it is used, so mostly in automobiles and heavy machinery, those kind of stuff. The types of couplings you have muff, muff or sleeve type, protected, unprotected, and bush and pin type. So in these things, then here, so these three, the muff coupling, uh, and protected and unprotected. So all these we called as a rigid coupling. So these come under rigid coupling. So rigid coupling, why? Because they don't allow any kind of relative motion between the two parts. You don't have any relative motion between those two, and only the push and pin type is one which is flexible. So this is a flexible coupling. So flexible coupling just means it's not very flexible or those kind of things, but a little bit. So maybe like 5 degrees or even 5 to 10 degrees of variation is allowed. So that's called a flexible coupling. A little bit of freedom you have in terms of motion. Suppose you say in automobiles, so it is subjected to vibrations, right? Vibrations, you have humps, and it has to take some amount of linear motion perpendicular to the ground. So those kind of applications you can use a flexible coupling. A little bit of freedom is there, but in case of these three, there is very rigid. There is no freedom in terms of any axial motion. So they are purely transmitting the torque from the shaft, right? And also there is Oldham's and universal coupling. So these are again, they're flexible in nature. So these are also coming under flexible couplings. That means they can permit a little bit of motion, not much, but a little bit of motion. So we'll be primarily designing these. These are called flange couplings. So these are flange couplings. Okay. So again, I told you there are two types. So this is a protected and unprotected. So what is protected and unprotected is, you can see these bolts here. So these bolts here, they are not protected. So they are outside of the flange diameter here. Whereas here you have some kind of protection for the bolts. That's the only difference. Nuts and bolts, you have some protection. So this is coming under protective. This is protective and this is unprotected. We need to make that also as protected. Protective. So this is protected. Protected in the sense only the bolts, no, they are inside. Protected, bolts are outside. That's the only difference. and a little bit difference in the design procedure probably. That's it. That's all the difference you will get. So, and this is what primarily will be designing in this also. These are all different dimensions. Don't need to worry about this. Is just an unprotected kind of plane which will be designing. So this includes even the key. You can see the key also here. Once we complete the some numericals on keys, we can move on to how to design a coupling like this. It's very simple. You have to follow some series of steps and find out the values. And this is a protected type. You can see there is a protection. This is a hatching cross section of the plane. You can see the bolts they are protected inside some covering. Okay, inside the flames, they are completely inside the flames. Therefore, they are protected. Similarly, these are all the dimensions, and what are the parameters of different things. We'll see this when we start the numerical problems. And the difference between these two is alignment, rigid and flexible. So as I told you, Oldham's coupling, all these bush and pin type couplings, and universal coupling, they are coming under flexible couplings. So in case of rigid couplings, you have bush and pin type. No, sorry, not bush and pin type. You have flange coupling, marine type, sleeve and coupling, or muff coupling. So all these things come under rigid. So what is the thing is, it has to be perfectly aligned. So that's the word here. It has to be perfectly aligned, and here a little bit of misalignment is allowed between the two shafts. And in the second one, it is used for motion free from vibration. So it is free from vibration and shocks, because since it is rigidly bolted, it is free from all these vibration and shocks, and it can run. It's more efficient compared to this thing. So, but this allows some amount of vibration and shock to be present. Okay, so wherever you have dynamic applications like automobiles, you use this, and wherever you have static applications like transmission of motion between one uh, part, or which are stationary in nature, so those cases you use rigid. So here no flexible, and here flexible elements are used like rubber bush and all those things are used. Flexible elements, some with a very low modulus of elasticity. Those kind of parts are used in flexible, whereas in here there are no flexible. All are very rigid and solid components. So this is just the first point. No misalignment here. Misalignment is allowed. So it can tolerate up to 0.5 lateral or axial and 1.5 degrees in case of angular misalignment. So this cost is less because low maintenance and no wear and tear of parts very often, but here it costs more. So this is over long run. Although you can say that rubber and all these stuff are cheap, but in operation these cost more. In case of maintenance and stuff, these are expensive. So if you take this thing in a long run, they are very efficient. Okay, you don't need to replace parts as often. Just lubricate once, and they'll run to many cycles. So as I told, the examples, these are protected and unprotected, universal bush and pin type. So mostly we'll be doing the protected and unprotected type couplings, and also the keys. Okay, the complete designing of keys and stuff. That's what I have decided for this class. Okay. So any doubts you have regarding the introduction, you can let me know for keys and couplings. So we'll start off with one simple problem. Fine. So we'll start off with one simple problem. Okay, today. You have a rectangular sunk key 14 mm. It is required to transmit 1200 Newton meter. Okay, let's see what is given. So it is a rectangular sunk key. So let's say it is rectangular like this. Okay, you have a rectangular key and rectangular key 14 mm in breadth and 10 mm in thickness. So we'll say this B is 14 and H is thickness 10. So these notations, no, you can directly go to data handbook. It is readily available, and it is required to transmit 1,200 Newton meters. So torque is given. That is say MT is torque 1,200 Newton meters is given. So write this in mm. You get 1200 into 10 power 3 Newton mm. So notations you can we can follow the original one. Don't need to revert. Wide 10 mm and thickness 75. Thickness 10 mm thick, that is given, and 75 mm long. So length is 75 mm. So all dimensions are given. And what is he asking us? Determine whether the what is that? The torque from a 950 mm. 950. And I think it's D from diameter 950 mm. Diameter of shaft D is 50 mm. Dia solid shaft. Determine whether permissible shear stress, crushing stress is sufficient for 56 megapascal and 168 megapascal respectively. So it is given as shear stress and crushing stress. So there is some fold over here. Shear stress is this much and crushing stress is this much. Okay, let's write the notations then. So shear stress is, I'll write tau is 56 newtons per mm squared, and this crushing stress. So the sigma B is B dash is 168 newtons per mm squared. So this is shear stress and this is crushing. Okay, so the question just asking us whether it is sufficient or not. So these dimensions, no, ultimately it will come to dimensions only. Length is this much, breadth is this much, and height is this much. So whether these dimensions are enough or not. So that is what the question is asking us. Okay, whether this satisfies the maximum requirement of stresses, right? Let's solve this. I'm just gonna copy this. Okay. Paste that. Right. Okay, I think we are ready. Okay, so we are zoomed in. We are ready with thickness. Right. Okay, so let's start this off. So we have, I told you before, they have only two equations to refer to this. There is uh, let's go back to the dead end. Just have two equations for this. Here, width of keyway. Okay, we'll just keep the length constant. Okay, using this equation. Let me copy this. Width of the keyway. Here, copy. Okay, so let's use this 19.5 equation and let's find out. So let's keep b constant. B is given 14. So this 14 equals 2 into dot empty. Is empty is given. So 1200 into 10 power 3. 1200 into 10 power 3 divided by tau. Shear stress maximum is given 56 into d2. D2 here is nothing but diameter of the shaft. This is 50 mm. So this is 50 into L, will keep it as it is. Okay, so L will keep it as it is, and oh, there's another D. What is that? D. Okay, so we'll pause it. We'll pause it here. We will continue this in the next